Welcome back everyone to another Precalculus lesson. In this lesson, we're going to finish off our conversation in Chapter 4, where basically in Chapter 4 we've introduced the basics of trigonometry, and we've spent a lot of time introducing the 6 basic trig functions, talking about how they look, how we can find their inverses, and everything in between. What we want to do now is, much like we did back in Chapter 1, we want to now see if we can sew all this information together and actually start to solve some real-world problems. I will make a small note here as we go through this content. Since we do not have calculators allowed in this class, for every single one of these problems, we're going to leave our answers as a combination of trig functions and their inverses. And you'll see what I mean as we do a couple of these examples together. The first example I want to come up against is the following. Here's a triangle that is somewhat incomplete. We seem to have knowledge about, say, 2 of the angles, but we're missing a third, and we have knowledge about 1 of the side lengths, but we're missing the other 2. And we'd like to use basic right triangle trigonometry to deduce what the missing side lengths and the missing angles are. So for example, the first thing I can note is if I isolate this angle that we do know, which I might give that angle a name, let's call it capital A, I know that, say, the sine of that angle is going to be opposite, a known value, over hypotenuse, an unknown value. And as long as we identify a relationship that has 2 knowns and 1 unknown, we can solve for the unknown. So the first thing we can observe is that if I take the sine of 62.7 degrees, where note, a lot of these real-world examples, the real world has not yet caught on to the fact that radians are the superior angle measurement. So for a lot of these angles, or a lot of these problems, we're going to be using the degrees because unfortunately that's what the real world uses, so we need to be comfortable using them as well. Sine here is going to be equal to opposite over hypotenuse. And if we solve for c here, we'll get that c is equal to 8.4 over sine of 62.7 degrees. Now if you had a calculator, you could actually compute what this value turns out to be, but again, for our purposes in this class, this is going to be a more than sufficient final answer. This is an answer involving trig functions. So this is how we found C. Maybe what we'll do next is figure out what the angle B is. Well, we know that the sum of the angles within a triangle is equal to 180. So if we know 2 of the angles, C and A, we can figure out what the missing angle B is. So since the sum of the angles, A plus B plus C, is equal to 180 degrees, we find that B is equal to 180 degrees minus A and C, which is going to be 62.7 degrees and 90 degrees respectively. In this case, quick computation gives us 27.3 degrees. And the last thing we need to find is little b, but if we already found little c based on our work earlier, we have actually 2 ways to find little b. We could, now that we know little c, use the Pythagorean theorem to solve for b, and we'll get that b is equal to the square root of c squared minus 8.4 squared. However, this is not a good way to do it, because our answer, and whether it's correct or not, if we do it that way, is dependent on whether we actually got the correct answer for little c. If we made an error with little c, using little c to figure out little b is going to perpetuate that error. So if there's a way to find new values like little b using only the information that was given in the actual problem statement, usually that's going to be a better choice. So for our purposes, the information given in the problem statement is the angle A and that side length 8.4, which now if we want to relate 8.4 and little b, we know we can do so by the trig function tangent. So we're actually going to not use the Pythagorean theorem and instead use a tangent. So what we're going to do is we'll get that the tangent of 62.7 degrees is equal to 8.4 over b. So then little b is equal to 8.4 over the tangent of 62.7 degrees. So there's small little micro decisions like that you have to make along the way, and over time as you develop more practice with this, you'll make the correct decision at every single one of those junctures. But it's important to remember that when given the option of either using information you found or using information that was provided, you always want to go with the latter. Sometimes our problems are going to get a little more complicated than that. Notice, right, by the way, these don't very much seem like word problems or real-world problems. Hopefully we'll start to identify why we're doing this as we proceed. So here's an example of we have two triangles with a handful of angles and side lengths, and we want to figure out what the length x is here. Well, now that since we have two different triangles at our disposal, we actually have a lot of different trigonometric relationships to work with. In order to use any of them, though, we do have to be clear. It might be worth noting that each of these triangles have their own vertical heights. Maybe I'll call them y and z respectively. So then the quantity I'm looking for is going to be y plus z. The reason I do that is because this big triangle up top, I have y, which is what I'm looking for, an angle, and then an adjacent 500. I know that here that the tangent of 40 degrees is then going to be equal to opposite y over adjacent, which is 500. This tells me that y is equal to 500 times the tangent of 40 degrees. Similarly, with the other triangle, the tangent of 25 degrees is equal to z over 500, which gives me a similar solving of z equals 500 times the tangent of 25 degrees. So the length in question, x, I now easily deduce as y plus z is going to be the sum of these two quantities. And if I factor out that 500, I might get something like 500 times the quantity tangent of 40 degrees plus the tangent of 25 degrees. Where this is a perfectly valid final answer, because again, we're allowed to leave our answers in combinations of trig functions. So this is a good example of how we can use intermediate variables like y and z that we came up with ourselves in order to yield an appropriate conclusion for a desired length, in this case, x. However, just as we can take a given triangle and put a triangle we can add a triangle to it, we can also encounter situations where this added triangle is actually somehow embedded inside of the given triangle. Predictably, when we do that, instead of adding these tangents, probably we're going to have some subtraction involved. Let's take a look. Here we have two triangles nested inside of one another, where we have a smaller triangle that makes an angle of elevation down here of 25 degrees, and then we have a larger triangle which makes an angle of elevation of 28 degrees. Each of which sharing the same base length of 600, and we're interested in sort of this small length x. The approach to this is going to be super similar to what we did before. Each of these triangles, the big triangle and the little triangle, are going to get owed their own independent intermediate variables. So maybe we'll call the little triangle's length b and the big triangle length a. And so clearly now the little length x is going to be the total length a minus b. So very similar to the previous problem, but instead we have some subtraction involved. But with these intermediate variables, what we end up with is tangent of 28 degrees, which is the larger triangle, is equal to opposite a over adjacent 600, as well as tangent of 25 degrees is equal to its opposite b over its same adjacent 600. And so solving for a and b, what we find is the desired quantity x is going to be a minus b, which then after factoring out the 600, we'll be left with 600 times the quantity tangent of 28 degrees minus the tangent of 25 degrees. So we witness that the answer form for this problem is eerily similar to the one we encountered in the previous problem. But instead of adding tangents, we subtracted tangents. So with these problems developed, we can now answer maybe some real-life questions. So here's an example. The word problem says, from a point on level ground 80 feet away from the base of the Eiffel Tower, the angle of elevation is 85.4 degrees. We'd like to approximate the height of the Eiffel Tower. Now, the first thing you have to do when you look at this is you have to draw a picture. So maybe this is the Eiffel Tower right here. There we have some Eiffel Tower looking structure. And we have a magic point all the way over here to the left. And what we've determined is that we are 80 feet away from the base of the Eiffel Tower. So this length is 80 feet. We know that the angle of elevation to the top of the Eiffel Tower is 85.4. So what that means is if you start looking horizontally and then you turn your head up until you see just the top of the Eiffel Tower, you've angled your head up 85.4 degrees. So that means this angle is 85.4 degrees. And so what we'd like to do is approximate the height of the Eiffel Tower. Fortunately, we can do that. The relationship between the given angle, the desired quantity h, and the given length 80 is clearly a tangent relationship. So we know that the tangent of 85.4 degrees is equal to h over 80 feet. The units here are super important, because at the end of the day, this is a real-life problem, and we want to give our answer in real-life units. So if we solve for h, we get that the height of the Eiffel Tower is approximately 80 times the tangent of 85.4 degrees feet. This feet is really important, because if you just write 80 tangent of 85.4 degrees, the observer doesn't know if that's feet, meters, inches, etc., etc. Now again, just like we did previously, we're not going to use a calculator to actually approximate this value. We're just going to leave it in this so-called closed form. This is something you can easily compute on a calculator or something. What we're doing here is the mathematics. Plugging that into a calculator is something a computer can do. So this is going to be our first real-world example of using trig to actually solve real-world problems. Oh, and by the way, if you're curious at all how angles of elevation can be deduced, there do exist very simple, basic tools that allow you, so I can think of, for example, I think it's referred to as a compass or a sextant or something like that, that allows you to start at level ground and then look upward to a particular area, to a particular height, and then it determines the angle of elevation. So this is definitely something you can compute without necessarily needing computers or something like that. And basically all of the questions we're going to run into are going to be some combination of drawing a triangle, and then I'm going to give you different pieces of data. Either I'll give you, the hypotenuse and the height, and you need to find, the angle or something like that. But basically that's what it boils down to. So let's take a look at this one. Here we have a guy wire that is 13.8 yards long, and it's attached to the ground, from the ground to a pole. So a guy wire is, for example, this might be our pole all the way over here on the right. A guy wire is some sort of a very strong cable that's attached to the top of some sort of a pole structure and gets connected all the way down to the ground. And usually that guy wire is very taut. So in this case, the guy wire is 13.8 yards, and apparently it's attached from the ground to a pole and the pole is 6.7 yards above the ground. And the question is, what is the angle that the wire makes with the ground? So what is this angle right here? Well, the relationship trigonometrically between theta and the given data, if this is to be a right triangle, is of course a sine relationship. So we know here that sine of the indicated angle theta is equal to opposite 6.7 yards over hypotenuse, which is 13.8 yards. The yards cancel. This angle is then going to be equal to what? Well, how do we start with something like sine of theta equals a quantity and then gain access to that theta? We have to undo the sine, and the best way to do that is to take the inverse, the arc sine of both sides. So here I'm going to get the arc sine of the left-hand side is equal to the arc sine of the right-hand side. Now the observation is that the arc sine of the sine will cancel because this angle is of course in quadrant 1. And so that tells us at the end of the day that the angle theta is equal to whatever the arc sine of 6.7 over 13.8 is. So we see here that trig functions are also coming into play. And so when we talked about in the very first page, this idea that we're going to leave our answers as combinations of trig functions, yes, but also their inverses. We see now an example of that, where if our goal is to solve for an angle, we have to leave our answer in terms of the inverse sign, in this case, otherwise known as the arc sine. So let's take a look at another example. Here we have that we are standing on level ground 800 feet away from Mount Rushmore. So immediately I start drawing a picture. Here's Mount Rushmore. Here's Abraham Lincoln's face. Maybe he has a nice beard and probably some sort of a top hat. Although, there we go. I know he doesn't have a top hat in Mount Rushmore, but you know, when you're given an opportunity to draw a fancy picture, you want to draw a fancy picture. So, there's our Abraham Lincoln face. We are apparently standing 800 feet away from Mount Rushmore. And we see that the angle of elevation to the bottom of the sculpture is 32 degrees. So maybe that's right there. So that's going to be 32 degrees. And the angle of elevation to the top of the sculpture is 35 degrees. So maybe to the top of his top hat, that's going to be 35 degrees. These are right triangles. And so the question now is, what is the height of the sculpture of Lincoln's face? So what is this height right there? The process for solving this, we've actually already discussed it. Because if you look at this picture, it's basically the same picture that we drew right here. Only difference is here I gave you the triangles and told you the angles and then had you solve for x. But the real world problem might very well be that this x is the height of a face on Mount Rushmore. So solving this is going to be much the same way. What we know now is that we're going to introduce some auxiliary variables. So maybe the little triangle is going to have an A, the big triangle is going to have a B. So what that means is that the tangent of the big triangle, 35, is equal to B over 800, again feet, units matter, as well as tangent of 32 degrees is going to be equal to A over 800 feet. So that x is clearly equal to b minus a, which is equal now to 800 times the tangent of 35 degrees minus the tangent of 32 degrees feet, where again units are very important here. So this is a good example to showcase why some of those more abstract looking problems we were solving in the beginning were actually not that abstract at all. They actually came from real-world problems. Now, so far we've used the vocabulary of angle of elevation to describe that if you're looking horizontally, that tells you the angle you have to incline your view in order to get to a desired viewpoint. There is an opposite idea. Instead of making your view go up, you could have your view go down. That's referred to as an angle of depression. This example highlights that. Here we have a helicopter hovering 1,000 feet above a small island. So here we are. This is our small island. It's got waves. There it is. Maybe it even has a palm tree. Let's draw a palm tree, shall we? Ooh, can't draw. Let's see. Oh, look at that. We got some coconuts and some palm fronds. Fantastic. It's important to have fun. Anyway, there's a helicopter 1,000 feet above the island. So 1,000 feet above the island, there is a helicopter, which again, we're also going to draw. Why not? So we might have something that looks like this. Okay, there's our helicopter. It tells us that the angle of depression of the helicopter to the closest point on the coast, which is going to be the coast of, say, mainland. So maybe this is the mainland over here. You know, we've got some sort of a actual genuine coast, and here we have sort of, maybe we have some office buildings or something like that over here, just actual, you know, places that people live and stuff like that. So here's the coast. So here's the closest spot to the coast, and what we find is that the angle of depression is if the helicopter is looking to the right, the question is how far does the helicopter have to look down in order to reach that indicated location. So here, if we draw then our line there, the angle of depression is this angle. That's 36 degrees. That's what angle of depression means. And so then if we complete the picture by drawing our right triangle here, the question is how far off the coast is the island? So that's going to be basically what is x here. And the important observation is that either you can solve for this angle, you could deduce, for example, that this angle right here is clearly going to be 90 minus 36, or you can remember that the angle of depression and then this angle down here to the bottom right are actually alternate interior angles. So you could remember that that's equal to 36 degrees as well. Regardless of which way you do it, you could solve then that x, or maybe we'll write it this way, we'll say that tangent of 36 is opposite over adjacent. So we could say that the tangent of 36 degrees is equal to 1,000 feet over x, which tells me that x is equal to 1,000 over the tangent of 36 degrees feet. That's a perfectly valid answer. If, however, you went with 90 minus 36, you'll end up having to use, you'll still use a tangent, but it'll look somewhat different. But you'll still get it'll be the same numeric value at the end of the day. So this is another example of how we can use trigonometry to help solve some real-world problems. Here's another example that's very similar to the Mount Rushmore example. We have a hot air balloon that's rising vertically. From a certain point on level ground, 125 feet away, from the point directly under the passenger compartment, we have a particular angle of elevation. And then as the hot air balloon goes up, the angle of elevation changes. The question is, how far did the balloon rise between those observations? Well, we had our initial viewpoint, which is sitting 125 feet away, And then initially we had the hot air balloon, and the angle of elevation to the bottom of the passenger compartment was apparently 19.2 degrees. And then it went up a little bit. Maybe it went all the way up in here. There it is. And that observation has an angle of elevation of 31.7%. And the question is, how far did it go up? What is this length right here? This is essentially the same exact question as the Mount Rushmore question. We have two different triangles, and these are both right triangles. We have two different triangles, and so we're going to give them intermediate variables. The one down here we'll call A, and then the large distance of the big triangle we'll call B, so that we can determine that the tangent of 19.2 degrees is equal to A over 125 feet. The tangent of 31.7 degrees is equal to B over 125 feet. So x is apparently equal to B minus A, which we know now is equal to the 125 times the tangent of 31.7 degrees minus the tangent of 19.2 degrees, and then we'll use our units. We'll call them feet. Again, units, very important. But while the exact description of the problem here is notably different from the Mount Rushmore problem, the structure is basically the same. So this is where we're going to pause the first video. The next video is going to pick up where we left off here, and then we're going to go through a few more examples of utilizing trigonometry to solve real-world problems.